Okay, so last lecture we talked about ways of fixing aberrations in your optical systems that you're building, which is changing your lens orientation, um, buying lenses that have less aberrations in general. And then at the very end, we talked about how you can use combinations of lenses to lower your aberrations, right? Another option for fixing aberrations is to talk to an expert. So let me add a layer here. Unfortunately, if you go talk to an expert, well, at least in my experience, a lot of experts don't know how to talk to people who have very little training in optics. And so you have to be able to talk in their language, which means you have to tell them how little aberration is acceptable, right? How little is acceptable. There's probably an E there. And there's and actually this is useful for you too, as you'll find out in your midterm design project. Then when you're correcting aberrations, it's really good to be able to have a number to compare things to, right? We're engineers, we solve problems with numbers in general. And so we want to be able to measure the amount of aberrations in our system, and then we can use that to compare two different systems and see if one is better than the other. So there's two ways to do this. One is through what we call wavefront error, and the other is ray error, right? Both are functions of the exit pupil. So both are functions of the height of the ray in the exit pupil. Let's first talk about wavefront error, and then we'll talk about, actually, let's talk about ray error first, right? So with ray error, if we we're going to use green lines here. Let's say they're supposed to focus to this point right here, right on this optical axis. As we know, the rays that go through, that are closest to the optical axis, are going to be the least aberrated. And so they're going to go through there. But as you saw in your optical designs, as you get farther out in the exit pupil, these rays are going to, I'm exaggerating it a lot here, are going to intersect the optical axis closer and closer to the lens, or maybe even farther away, right? It's totally possible to have negative spherical aberration as well, or negative aberrations, which are different than what we've been experienced here. But with relatively simple systems, you're going to experience positive spherical aberration like this. So one way we can measure this is to compare where the rays intersect the optical axis as a function of their height, h, going through the pupil. And so if we were to plot this, what we would plot is we would take our x and y axes like this, and we would say, all right, so traditionally this is still our height, h, in our pupil, and then this is our error in this direction here. So we would plot for this one, we would plot a point. Our error for our exactly middle ray is 0. Actually, let's do this in green. Middle ray is 0, and then as we go up to our next ray, which is here, we have some error. We do our next ray, which has even more error, some even more error, and then finally a tremendous amount of error. And if we connect those two, we can plot them. And this is our ray error. And this is actually called our longitudinal ray error. We can also plot the transverse ray error, which is if we take a plane through where we ideally think the focal plane should be, which is where the paraxial or the rays closest to the optical axis intersect the optical axis. And we can say, okay, well, how those intersect the optical axis at 0, the paraxial rays, all the other rays intersect them at other places. So that distance grows for all of these rays here. And so we can plot the transverse ray error in the exact same way, right? So as a function of our pupil height here, and we'll plot this in green as well, we can say, all right, well, the first one is 0. The second one is exiting or intersects our this axis here, this plane, at a height of this one. So it intersects it like right there. And again, I mean, this is going to look relatively similar to the other one because for a simple system like this, transverse and longitudinal error are obviously quite related. But this gives you an idea of the spot size on your camera, right? So if you limit your aperture to say, let's say we limit our aperture stop to here, we know that our spot size is going to be at least this big across, right? And if we open our aperture up all the way, then our spot size is going to be this big, which is a lot bigger, right? So the traverse rate error gives us a really good way of telling exactly how fuzzy our image is going to be based on our aperture size, right? Which, as we know, is related directly to our F number. Because as you decrease your aperture size, you're going to decrease the size of your exit pupil, which means you're going to decrease the D and the F over D that makes up our F number. So there's a cost for doing that, right? We decrease our aperture size, which means we decrease our amount of aberrations, but also we are increasing our F number, which means we are decreasing the amount of light we are collecting. Excuse me. So traverse ray error, really intuitive, right? Longitudinal ray error is also very intuitive, slightly less easy to interpret, but a little bit more easy to calculate, right? The other method that we could use is something called a wavefront error. Now, wavefront error is slightly more difficult to calculate from ray tracing. Not a tremendous amount, but a little bit. And the way it works is we say, all right, the wavefront is defined as a plane that is perpendicular to the rays at all points. So before the lens, we have a parallel beam of light entering our lens. And that parallel beam of light is going to result in a plane that is perfectly flat and parallel, right? So at all points, it is perpendicular to our rays. And that means if we have a perfectly flat plane, we have a perfectly parallel beam that's going to travel. Well, we'll learn about this in diffraction. It won't travel parallel forever, but if we just pay attention to ray optics, it's going to we will think it will travel parallel forever. That's great. After it goes through the lens, this wavefront gets deformed in a very particular way, right? In an ideal world, let's draw some ideal world rays here, which are the red rays, right? We would expect our, oops, let's undo that. We would expect all of our rays to intercept the focal point, right? And since all of these rays are going through the same point, a plane that is perpendicular to each ray is going to form a circle, right? So if we draw in red the plane that is perpendicular to all of these points, it's going to look like an arc on a circle, like that. It's perpendicular to each of these points. Now, obviously, this arc of this circle is not perpendicular to our green rays, which are our actual aberrated rays, right? So we can do the same thing. We can calculate the plane, we'll do this in green, that is perpendicular to these to the green actual rays. And what we see is that it actually curves a little bit more. And this is perpendicular at each point. And the distance in between these two planes here is our wavefront error. And so we can plot our wavefront error. Usually it's plotted in 2D actually, but we can plot our wavefront in 1D like this, exactly as we did it with our traverse ray error. So we can say, all right, well, this is our H, this is our aperture, and then we can plot our wavefront error here. And usually we normalize it by lambda, our wavelength. So it's the units has no units, right? It's unitless because it's normalized, but we do it in multiples of lambda. And in this case, our wavefront error is going to result in a negative curve like this, right? Um, where as we increase our height, we increase the amount of error in our wavefront. So yes, these all look the same for here, but with more complicated systems, I assure you that these will stop looking the same. Your traverse ray error and your longitudinal error can actually have some really interesting shapes. As you get what we call higher order aberrations, you can get curves that come out and then back in and then out, right? Um, and this results from adding extra lenses, trying to correct some aberrations, adds others, and it becomes kind of like a whack-a-mole thing. Um, you, yeah, whack-a-mole in the sense that it's impossible to eliminate them completely, and then as it gets more complicated, you get these little ripples that become increasingly difficult to remove. The same is true of our wavefront error. Now, if we plot this in wavefront error in 2D, perpendicular to the rays, we know that. We'll talk about how to calculate this when we go to the Jupyter Lab notebook that I made that shows you guys how to calculate these things. The important part, though, we'll talk about it in like overview here, is that for each of our rays, what we're going to have to do, like here is a ray coming in, and then that ray goes through our focal point down here. We're going to have a previous point on our plane that we've already solved for right here, let's say, along with a previous ray. So let's draw our previous ray real quick, like this. So let's say our wavefront is going something like this right now. We're going to find a ray that is perpendicular to this ray, perpendicular, and then we find where it intersects the next ray. And then that's the next point on our plane that we're solving for, our wavefront. And then we just keep doing that. So we're going to have a whole bunch of rays like this. And each time we're going to find the perpendicular. So here's our new starting point. We find our perpendicular ray. I kind of drew that first one wrong, but that's okay. We find our perpendicular ray. We find the new intersection, and we find a new perpendicular ray, find its intersection, find our new perpendicular ray, find its intersection, and keep going along until we've run out of rays. Now, obviously, this gets more accurate because we're doing an integration here, a discrete numerical integration. This gets more accurate when your step size is smaller. So the more rays you have, the more accurate this gets, because errors in the beginning can not cascade, but accumulate, right? Errors accumulate when you integrate like this. So you want to use as many rays as possible to do these kind of calculations. All right, so yeah, this goes over how to do that. But like I said, I've actually made a Jupyter Lab notebook about it this time, so we'll just go to the Jupyter Lab notebook. So typically 1/2 to 1/4 lambda RMS is considered an acceptable amount of wavefront error. 1/2, half lambda to 1/4 lambda. So 1/2 of our wavelength to 1/4 of our wavelength. Root mean squared is considered acceptable amount of wavefront error. Generally, we don't report our max wavefront error because it can be misleading. You can have one region that has a lot. Like I said, the shape of these wavefront errors. Let me go back up here to where we plotted these before. This is a gentle shape, right? But we can have really kind of severe wavefront errors, which start off quite small and then increase very quickly at the very end. So if you report the maximum wavefront error here, that's misleading because over most of your aperture stop, most of your exit pupil, actually, you will have a very small amount of error, right? So we report the root mean squared in order to get an idea of how how all the rays are aberrated. The other thing you'll find out is that a lot of people report talk about wavefront error in terms of Zerniky polynomials, and that's because these are orthogonal polynomials which these are orthogonal polynomials, which remember, orthogonal is really useful because the whole reason Fourier series works is because each sine and cosine is orthogonal to each other, which means we can add them together without having redundancy, right? So these are useful for describing wavefront errors because it's a mathematically sound way to decompose wavefronts. So just like you would decompose a signal using Fourier transform, you can actually do a transform with these Zerniky polynomials, and they will tell you the strength of each of these different polynomials, these 2D polynomials, as part of the decomposition, right? It should be noted these are not exact representations of what these wavefront error, what these aberrations look like, but they're really quite close, and that makes them quite useful. And they're fast as well, which is why actually you can have real-time adjustments to your optical system if you put in adaptive optics. What they do is they take a known wavefront, decompose it into the aberrations like this, and then apply real-time changes to a deformable mirror to correct for those aberrations. So anyway, these are quite useful for that reason. And each of these Zerniky polynomials have, the order of these polynomials has a meaning, right? So we have tilt here. Tilt, so how much is your wavefront tilted? This could happen if like you're looking at if your lens, for example, is misaligned. Sometimes it can cause tilt. This is just defocus. These two here are astigmatism, positive and negative astigmatism. As we go down, we have coma. We have spherical aberration. We can actually have secondary astigmatism. Why did I do that? Let me undo that. That got confusing. Got confusing for me. It's going to be confusing for you. So we have these two here are secondary astigmatism. Remember how I said there are higher order versions of these aberrations? Well, now we're starting to get into those higher order versions where the shape of them is more complicated, right? Here, so our original astigmatism had just 4 lobes, negative, negative, and positive, positive. Our secondary astigmatism has 4 lobes, but then also an additional lobes right on the outside, right? So it has 8, it's twice as many. And it goes on, right? We have higher order coma, we have higher order spherical aberration, and then mixtures of the two. It gets quite complicated. But the main thing to remember is that if we decompose our wavefront into these polynomials, we find out that we have a very strong Zerniky, like 4th order 0 polynomial, then we know that we have a relatively large amount of spherical aberration that we need to correct for. People before this, people use Seidel coefficients, which are similar but not orthogonal, so their math isn't quite so nice, right? Yeah, so that's it in terms of language that people are going to ask you to talk about. Let's talk about actually measuring our wavefront error, like you're going to have to for our design project here, because we're going to actually ask you to make changes to your optical system and show that those changes are an improvement, right? So let's share my Jupyter Lab screen. Good. Okay. So I never noticed there's a simple tab. I wonder what this does. Oh, interesting. Okay. So we're going to talk about now how to measure aberrations, how to actually calculate them. So here we're going back to our 2-inch diameter, 100 millimeter focal length plano convex lens. We're plotting it. We plotted this before in a past lecture when we talked about aberrations. We know that there's a large amount of spherical aberration with these lenses. So what we're going to do, and I go into detail about how we do it, but we're going to go through each ray, right? And we're going to figure out where each ray hits the optical axis, and we're going to plot the distance from where the middle rays, these dark red rays, hit. Okay? So to do that, we have to figure out where our rays hit the initial heights of our rays, right? Where do our rays start from? Because remember, we're plotting all of our results as a function of our ray height as it goes through our aperture stop, or really actually through our exit pupil. So that height is important because remember, we can reduce that to reduce our aberrations. So we have to record our initial heights, and then we go through, figure out where it intercepts the axis. You did this on your first deliverable. You just didn't do it for all of the rays. So we just do a for loop here, and we do it for all of the rays. We figure out where the center rays intercept. We then subtract all that from all of our other rays, and then we plot our error, and we find out that our longitudinal ray error looks like this. And we have a tremendous amount of longitudinal ray error. We have 25 millimeters of ray error, which is huge. If you were in class the other day, we looked at some lenses where they talked about how they have tens of microns or hundreds of microns of ray error. We have orders of magnitude more than that. So we can flip our lens. We can see by visually that we have less ray error, but we can also plot our ray error for our flipped correct orientation of our lens, and we can see that we have less than half as much ray error now. That's awesome. Now we can go through and try to calculate our transverse errors, right? Which means we have to figure out where our rays intercept our ideal focal plane. And remember, our ideal focal plane is where our red rays intersect the optical axis, because those are paraxial, and paraxial rays have the least amount of aberration because they're the ones that are least deviated, least have the smallest angle, smallest angles with the normal when they go through the lens. So they're the ones that are least far from that nonlinear region of Snell's law. So if we go through, we do that. Basically, we just have to figure out where the rays exit, what direction they're going in, figure out how long it takes them to get to that plane, which is t here. We're using a parametric representation of these lines. So it's just the distance t, which is the distance to that plane divided by the direction cosine in that direction. And then we add that to our height from our original height that it exited the lens, and that gives us our final height. We do that for both of our lens orientations here at once. We plot both of them, and we can see that here our flipped lens has obviously less than half as much tangential ray error as well. So what this means, though, is we could pick a aperture stop intercept, so a width of our aperture stop. Let's say we pick 10 millimeters as our radius of our aperture stop. If we drew a line straight across, we could say, oh, well, that will reduce our error to looks like less than a millimeter with our incorrect lens, but we're on the order of like hundreds of microns with our correctly flipped lens. So one of the reasons why we're showing so much aberrations with this lens that we have here is because it's a 2-inch diameter lens, which means we have a huge pupil diameter, which means we have a lot of error. Now, if we're trying to calculate wavefront error, and again, I'm going to expect you guys to go through this in much more detail than I'm going through it, simply because you're going to have to for your midterm design project. We will again iterate through each of these rays. I don't know if you guys can hear my son, but he's climbing up the stairs. We're going to iterate through all of these rays, figure out the direction that is perpendicular to each of those rays, figure out the distance to the next ray, and then add that distance along the perpendicular direction to our locations and store that new location. If we do that and we plot our wavefront, here's half of our wavefront. We can do the same for our ideal spherical wavefront, plot the two of them together, and the difference between the two is our wavefront error. And we can see that our wavefront error here, when normalized with respect to our wavefront, is actually on the order of thousands of our lambda, which is unacceptable, right? We want it on, a good system is on the order of 0.5 lambda. So ours is more than terrible. Cool. So I will post this notebook to UB Learns, and then look this over, and then you'll start using these calculations on your previous designs, and then start using stock lenses from Thor Labs to improve your design.